All right, let's get going. So this week is going to be about lenses. So continuing to draw ray diagrams and thinking about images. In this case, though, now we're going to be talking about lenses. So lenses, right, make images out of bent or refracted light. So we have to come up with a way of figuring some things out like focal points and some key rays that we can draw so we don't have to try and calculate refracted angles and things like that. Once we have lenses down, we can get into some optical systems that we use in our everyday life, like how do eyeglasses work, what kind of lenses work in eyeglasses, how do we put together things like telescopes and microscopes. And so by the end of today, we'll have finished up what we need to for geometric optics. So one of the first equations we come up with for lenses is an equation that will tell us the focal length of the lens depending on its shape. So this is the lens maker's equation. If we know the shape of the lens, so we know the radius of curvature of the front and rear face of the lens, and we know the index of refraction of the material that I'm making the lens out of, we can identify the focal length. So probably the trickiest thing about using the lens maker's equation is figuring out the radii of curvature and figuring out the sign convention attached to that. So with sign conventions for lenses, if the rays are coming from a certain side of the lens, we call that the front of the lens. And we consider a positive focal length to be behind the lens. So if we have a radius of curvature that is coming from a center point behind the lens, we're going to use that same sign convention we use for focal length. So if the center of curvature of a particular face is behind the lens, then we say that that radius of curvature is positive. So for a crescent lens like I've drawn here, when we put the radii of the front and rear face into the lens maker's equation, both of those values are positive. Meanwhile, for a convex lens, which is probably one of the more common shapes, we consider the radius of the front face to be positive, since the center of curvature is behind the lens. And we consider the radius of the rear face to be negative, since the center of that curvature is in front of the lens. So when I go to put the convex lens into the lens maker's equation, R1 would be positive, R2 would be negative. So let's dig into what we have when we talk about a positive or a negative focal length. So if we have a positive focal length, it means that parallel rays are going to bend to a point that is behind the lens. So this is what we think about when we talk about converging lenses. Parallel rays come in and they bend, they converge to a point. So if we had a focal length that was in front of the lens, then parallel rays would come in and then they would diverge from that point in front of the lens. So when we think about a positive focal length, we're thinking about a converging lens. And just like with mirrors, the focal point is the location where parallel rays are bent to, right? So if I have an object that's infinitely far away, it'll create an image at the focal length in the same way it did for curved mirrors. And if I have an object at the focal length, it would lead to an image that's infinitely far away. So one thing that I want to highlight here that's going to come back later on in the talk is an image that infinity is perfectly visible and in fact oftentimes really useful. So our eye, right, one of the pre-topic videos talked about how the eye works. The eye is at its most relaxed when it's looking at something that's quite far away. So the sun and the moon are effectively objects that are infinitely far away, and we can see them, our eyes can focus on them just fine. So if I want to develop an optical device like a telescope or a microscope, I often want the final image to be created at infinity, because then I can look into the microscope with my eye muscles totally relaxed, meaning I can comfortably use my telescope or my microscope for a long period of time. So an image at infinity is not just perfectly visible, but often actually a desirable outcome for an optical device. Okay, so we have a couple of equations, right? We have the lens maker's equation, We have the thin lens equation, which looks really similar to the mirror equation. And it basically is the same equation, but with some different sign conventions that we just have to be careful about. And we have magnification, which again, looks like a really similar equation that we had for mirrors, and we just have to be careful about the sign conventions. So just like with mirrors, we want to draw ray diagrams. We want to use 3 rays, right? Because with 3 rays, it's really hard to make one mistake and then get the wrong answer. With 3 rays, if you make one mistake, they won't all converge in the same spot, and you'll be able to track down the mistake. So when we draw these ray diagrams, we're going to use 3 rays. The 3 rays we're going to use, number 1, we're going to have parallel rays bend to the focal point. Right, number 2, we're going to have rays through the focal point come out parallel. And ray number 3, the ray that goes through the center of the lens will pass through without bending. So if I draw my ray diagram, I want to flag the object, I want to locate the lens, and I want to mark 2 points. I want to mark the focal length, and I want to mark the negative focal length. So this is an example where I have a converging lens, and so the focal point is greater than 0. So the focal length would be behind the lens, right? The object side is always the front, and so the positive focal length will be behind. But for geometric purposes, I also need to know this point, which is the focal length away from the lens, but on the front side. So I tend to call this negative f, just to make it clear which of the 2 points I'm using. So geometrically, for lenses, both of these are going to be important, but I want to keep track over which one is my positive and negative focal point. If you label them this way, then when we get into diverging lenses, it's a little bit easier to figure out how to draw those ray diagrams, and we can maintain these same sign conventions. Okay, so a parallel ray comes into my converging lens and bends through the focal point. A ray that passes through the focal point comes out parallel. And in this case, we're going to use that negative focal point. So we're going to say that a ray that passes through the focal distance on the front of the lens, that ray comes out parallel. And so I can see by drawing these 2 rays, I have some nice symmetry here. So geometrically, right, this makes a lot of sense. My 3rd ray is going to go straight through the middle of the lens and not bend. So I can arrive at my image, right, by looking to see the point where the 3 bent rays converge. Okay, so one of our problems was to sketch a ray diagram to find the image of a small object placed 8 centimeters away from a lens, and we know the focal length of the lens. So in this case, the object is closer than the focal distance to the lens, so that means when I draw it, the object is going to sit between the lens and that focal distance on the front side that I've called negative focal point. So I can draw my rays. The parallel ray passes through the focal point. When I go to draw ray number 2, though, that gets to be a little bit tricky, right? Because I want to think about the ray that passes through the negative focal point. But if I just go from the object through the negative focal point, right, that doesn't actually pass through the lens. So we want to use the same trick we did for mirrors, where really I just care about maintaining the geometry of that line, right? I use the negative focal point and the top of the object as 2 points to describe a line, and then that's the ray I'm going to draw to the lens. So then that ray that is geometrically coming from the focal point on the front of the lens, that ray comes out parallel. So when I see this ray diagram, the first thing I think is that, well, my bent rays don't cross, so I have no real image, and instead I have a virtual image. So I can trace those bent rays back and locate the virtual image. I can see it's going to be right side up, and I can see it's going to be larger than the object. If I break out the thin lens equation, right, I know that the object distance is 8 centimeters, the focal length is 16 centimeters, and I get that the image distance would then be a negative 16 centimeters. So the sign convention here for a negative image distance is going to be in front of the lens or virtual. A positive image distance would be behind the lens. I can use the magnification equation. I get 2. I get a positive 2, so a positive, if I use the sign convention, is going to be a right side up image. Okay, so let's look at a diverging lens. So for a diverging lens, the parallel rays are going to bend through a negative focal point. So you can see I've drawn, because the focal length itself is negative, the focal point is in front of the lens. So my negative focal point is now on the far side of the lens. It's important to keep this distinction because if you remember, the rules we had for drawing our rays specifically called for the positive or negative focal length. And it's easy to get those confused, so that you need to have some way of labeling, right, which is the positive and which is the negative focal length from the lens to get this right. So our diverging lens, we had a double concave lens, so that's going to be a lens that looks something like an hourglass. Each face has a radius of curvature of 35 centimeters. We know the index of refraction of the glass. We need to identify the focal length first. Then we can start using equations and drawing some ray diagrams to get a feel for the image. So for the focal length, we're going to use the lens maker's equation. And again, the trickiest part of the lens maker's equation is the sign convention for the radius. So I want to sketch the lens. I want to draw and identify the centers of curvature of the front and back of the lens. So the front face of the lens is like a circle with its center in front of the lens. So by our sign convention, that was a negative radius. The rear face of the lens, that was like a circle with its center behind the lens. So that was positive in our sign convention. So if I put a negative 35 centimeters in for R1, positive 35 centimeters in for R2, then I arrive at a focal length of a negative 44 centimeters. So negative tells me that this is a diverging lens. And so the focal point is going to be right somewhere on the same side of the lens as the object, right? So in front or near the radius of curvature for the front face. So when I use the thin lens equation to locate the image, I want to be extra careful here and make sure that my focal length is negative because this is going to be in front of the lens. And if I do that, then my image distance is also negative, telling me that this image should show up in front of the lens as well. So I'm going to end up with a virtual image in front of the lens. Notice that though the object distance is positive, and this is a little bit tricky. And since this is a practice problem where you don't get points off for making a mistake, I wanted to make this seem a little bit confusing, but you can't really put the object at a negative 0.66 meters if it's a real object, right? So the object distance in our sign convention is always going to have to be positive or this equation doesn't make sense. There is a very obscure exception to this that I'll bring up towards the end. But generally, right, the object distance, if it's a real physical object, that has to be a positive object distance. So we kind of know to expect a virtual image on the same side of the lens as the object, and that'll be a useful bit of reference going forward. So now let's look at drawing our ray diagram, because this is going to get a little bit tricky. This is probably the trickiest case to draw, but there are no new tricks. All of these tricks we've seen before. So the first ray, right, comes in parallel and bends through the positive focal point. For a diverging lens, the positive focal point is the focal point in front. So when I say bends through that point, right, I need to, again, draw a line that passes through that focal point, right, and then this ray is going to bend along that line. Ray number 2 is going to head towards the negative focal point, but it's never going to quite get there. It's going to hit the lens before then, and then refract parallel to the optical axis. The last ray, right, is the easiest through the center of the lens without bending. So these are my 3 rays for the diverging lens, right? I have to really be confident with, right, the idea of something coming from a place geometrically rather than physically and heading to a point geometrically, like along the line connecting that point without ever physically getting to that point. Because none of my 3 rays that I've drawn actually physically pass through any focal points, right? The bending through the focal point is meant in just a geometric sense. So once I've got my ray diagram, I can trace those bent rays back to find the point they diverge from, and that will give me the image. I can indeed see that it is a virtual image, which I would have expected from thin lens equation. It's upright and it's smaller. If you made that sign error I was almost trying to get you to make in the practice problem, this is the point where you could become suspicious, where, right, we can get the image here, and then the answer from your thin lens equation doesn't make much sense. So the ray diagram is a really useful tool for checking equations and vice versa, right? They should give you consistent answers, and it's worth looking for that consistency to see if you can identify where something might have gone wrong. Okay, so we talked a bit about the eye in the pre-class videos, so I want to talk a little bit about eyeglasses and how eyeglasses work with the human eye. So this isn't exhaustive, but the vast majority of eye problems correspond to being nearsighted or farsighted. Nearsighted is someone who has trouble seeing things that are far away. Farsighted has trouble seeing things that are close by. So these correspond to, right, challenges with the muscles in the eye, not being able to deform the lens of the eye enough to change its focal length enough, or not being able to relax sufficiently to restore the lens of the eye to its resting shape. So let's talk about for a nearsighted person. So a nearsighted person has trouble seeing things that are far away. So if I want to design glasses that helped someone like that, I'd be looking for, I have to identify like what kind of magnification would I want, where's the image going to be, and what kind of lens could I build that hits on those goals. So if I have trouble seeing things far away, then that means I would like a lens which makes an image that is closer to me than the object, right? So I want an image distance that's going to be smaller than the object distance. And this is the part that's a little bit tricky to think about, is I want a virtual image for a couple reasons. I want a virtual image because virtual images are going to be upright, and I really don't want eyeglasses to flip images around and make the whole world upside down. That'd be really inconvenient. And I want a virtual image because the last thing I want is an image between the lens and my eye, right? If you take an object you have at home and try to bring it closer to your eye, right, at some point you reach a point where you can't focus on the object. If eyeglasses made real images that were very, very close to the front of your eye, you wouldn't actually be able to focus your eye on those images. So I really want a virtual image that is located on the far side of the eyeglasses. This is especially obvious when I'm talking about contact lenses, right? Contact lenses sit directly on the eye. So the image they make has to be right outside the eye for the eye to be able to focus on it. So when I'm building eyeglasses, I definitely want to be making virtual upright images. So in this case, the diagram that we drew for the diverging lens satisfies all of these conditions, right? So it took an object that was far away, made an image that was closer. That image was virtual, upright. And so if I have a diverging lens, that's going to help out someone who is nearsighted. So if you do use corrective lenses, what's written on the front is called the power. I don't know why it's called the power and they don't just use focal length, but they call it power. It's just defined as 1 over the focal length in meters. Eyeglass makers and optometrists use power. They quote it in units of diopters. A diopter is just 1 over a meter. I don't know why they need to have their own fancy unit and their own fancy measurement that no one else uses. But anyway, that's what they do. They do power, which is 1 over the focal length. And so if you're nearsighted, your prescription will have numbers like -1, -2, -2.5, something like that to correspond to a negative focal length and a diverging lens. So for a farsighted person, then I'm going to have trouble seeing things close by, meaning now I'm going to need an image that is further away than the object. I still want a virtual image. I still want it to be upright. And so actually the first of the two ray diagrams, or I guess the second out of three that we drew today, was seems to hit all of these criteria. An image distance larger than the object distance, upright, virtual image. So I need a converging lens with a larger focal length, because I want the things I'm looking at to be between the lens and the focal length. Again, power is going to be 1 over the focal length. So if you have a prescription like this, it would be quoted in terms of positive numbers like 1, 2, 2.5, and those would correspond to just 1 over the focal length. Okay, so eyeglasses, right, use just a single lens, but when we want to build more complicated devices, we quickly need to start using more than one lens. And the reason for that has to do with this concept called angular size. So the idea of angular size is that how big something appears to you is not just related to how big it is, but how close it is. So we can define angular size in terms of how much of your field of view that the object takes up. So I can talk about the angle subtended by a person, right? So that would be some sort of angle, right? The tangent of that angle would be the size of the object over the distance to the object. And I can talk about, if I make an image, say in a flat mirror, that image is the same size and the same distance from the mirror, right? But it might look smaller because the image is effectively further away. So that looks smaller is angular size, right? The image is actually the same size, but it's further away. It's like the difference between, right, if you look at a car that's outside your window versus one that you're standing next to, right, it could be the same car, but it looks smaller because it's further away. If the angular size is very, very small, then we can use a small angle approximation and say that tangent of theta is roughly equal to theta in radians, but we certainly don't have to. So one thing that's kind of fun that showed up in the Poll Everywhere questions for this week is the idea that the sun and the moon are basically the same angular size, meaning that if the sun and the moon are both in the sky, they look to be around the same size to someone standing on the ground. But we know the sun is much, much bigger. And so we can calculate how far away the moon is versus how far away the sun is because they subtend the same angular size. So that's just kind of a fun thing to try. Okay, so another one of the poll questions for this week said that if I, right, you're not supposed to actually look at the sun. So if I have an eclipse and I'm trying to use a lens to make like an image of the sun on a screen, right, how big is the resulting image of the sun depending on the focal length of the lens? So the way that we actually go about figuring this out requires us to remember that the object distance of the sun is basically infinity. So the image is going to be located at the focal length. So the image distance should be equal to the focal length. So the angular size, right, of the image here is going to be given by the tangent of the angular size is equal to the height of the image over the distance to the image, which is going to be the focal length. The other thing I need here is this idea that a single lens is always going to maintain the angular size. So we can see that with any of the ray diagrams that we'd drawn so far today. So for example, if I look at the angular size of the image and the object for this lens, right, they're both going to share these similar triangles, right? Meaning that they're going to take up the same angular size. Even though the image is bigger, it's also further away. And with any single lens, it's always going to maintain the same angular size. So a single lens can give me a bigger or a smaller image, but it's never going to accomplish any angular magnification. So here, the angular size of the image is going to be the same as the angular size of the sun itself, right? So that's 0.5 degrees. And so I can get the tangent of 0.5 degrees is the size of the image over the focal length, right? And that's how I get my answer here. So if I say that the height of the image over the distance to the image is the tangent of the angular size of the image, right? And then I need the image distance is equal to the focal length, then I get a height of 35 centimeters. So I think I also asked a question that was like, what is the angular magnification of a lens with focal length 4 meters, right? It doesn't matter what kind of lens you've got. It's never getting an angular magnification different from 1. For one lens, the angular size of the object is always the same as the angular size of the image. Okay, so this is going to lead us to a discussion about optical devices that have more than one lens, or a lens and a mirror. If I want to achieve angular magnification, I need to have at least 2 optical elements to do this. So let's look at a telescope as kind of the easier of the 2 examples. So for a telescope, I'm going to be looking at something that's quite far away. So my object distance is going to be essentially infinity. And when I'm all done, I want to make an image that's easy to look at. So let's say I also want to make my image distance at infinity, right? Images at infinity, like I said earlier, perfectly visible, easy for the eye to focus on, right? With your eye muscles completely relaxed. What I want to accomplish, though, in the meantime, is I want a angular magnification, right? I have said this a couple times before, but if I'm looking through a telescope at a planet, the planet's pretty big. The image of the telescope doesn't need to be bigger than the planet, but it needs to be closer. It needs to take up more of my field of view. So I need an angular size of the image that's much, much greater, ideally, than the angular size of the object. So one way to build a telescope is to use 2 converging lenses. So whenever I'm using more than one optical element, I need to treat the image made by the first element as the object for the second. So this can get kind of tricky, right? And this was something that was a bit of a stumbling block for the microscope. But ideally, I want to locate the image from the first lens and then treat it like the object for the second lens. Now, for the telescope, one thing that makes this easy is that I'm always looking at something that's quite far away. So that means the image being created by the first lens is at the focal length of that first lens. And so typically for a telescope, we call the first lens the objective lens. So the focal length of the objective is also going to be the spacing between the first lens and the image. Now, if that's being treated as the object for the second lens, and I want the second lens to have a to have an image at infinity, right? I want the image distance to be infinity for the eyepiece. Then I want the object distance to be the focal length of the eyepiece. So that means the distance between my 2 lenses should always be the sum of those 2 focal lengths. So that means I'm always getting an image from the first lens in just the right spot to give me an image out of the second lens that's infinitely far away. In other words, I'm always getting parallel rays into my first lens. I'm always getting parallel rays out of my second lens. So if I want to go now and find the angular magnification, I want to identify the angular size of the object, right? So that would be, that could be represented as the focal length of the object, right? Comparing that to the height of the intermediate image. So the angular size of the object is going to be equal to the height of this image divided by the focal length of the objective, where the angular size seen by the second lens will be that same image, so the same height, but now over the focal length of the eyepiece lens. So now I can take the angular magnification as the ratio of those 2 angular sizes, and that's going to be equal to the ratio of the 2 focal lengths. So if I have a telescope made out of a lens that has a focal length of 10 meters and a eyepiece that has a focal length of 2 centimeters, right, I'm always going to be looking at the ratio of those two, 10 over 2 centimeters. That's going to be, right, 1,000 centimeters over 2 centimeters. So this is going to give me, right, a 500 magnification lens, or telescope rather. So the best telescopes I can make are just going to have a big difference in the focal lengths between the two lenses. The limiting factor, of course, is that the length of the telescope, right, has to be equal to the sum of the two focal lengths. So the length of the telescope would be 10.02 meters, and that's already getting pretty long, right? So ideally, I mean, I'd love to build, right, a telescope using like a focal length of 1 kilometer or something like that, but then I would need to build a kilometer long telescope body. So that becomes the limiting factor in building an optical telescope. Okay, so that leads us to our final problem for the week, which is the microscope. So the thing that makes the microscope tricky is that it's no longer looking at something that is really far away, right? The object for a microscope is now typically quite close to the lens of the microscope. So a couple things that are going to change is that the image from the first lens is not going to be at the focal length of the first lens anymore. And in fact, the location of the image from the first lens will vary depending on how far away this is. So if I'm using a microscope, I need to have a couple dials. I need to be able to adjust the location of the stage, right, to change the object distance. And I actually need to be able to adjust the barrel length of the microscope such that I can get a clear, easy to see image out of the second lens. So now the spacing between these two lenses is not just going to be the sum of the focal lengths. So to start with, I asked about the first lens. And the reason why I started talking about just the first lens is that wherever this image from the first lens ends up, that's going to be the object distance for my second lens. So I have to figure out the image from the first lens before I can figure out the whole microscope. So just looking at the first lens, the objective lens, I know the object distance, I know the height of what I'm looking at, and so I can try to figure out the location of the image, right, using the thin lens equation. So that's going to give me an image that's located at 130 millimeters. And I can find the linear magnification, right, looking at the height of the image over the height of the object. So that's going to be the same as the image distance over the object distance with a negative sign. So 130 millimeters over 5.2 millimeters gives me a linear magnification of negative 25. The negative is telling me that this image from the first lens is flipped upside down. So any people who have used microscopes before, right, a lot of microscopes do actually operate in this way where what you're looking at the end of the day is upside down, right? So sliding the stage around for a microscope can actually be a little bit tricky if you've never done it before. So, okay, I have a linear magnification. So that means the height of the image created by the first lens is 25 times bigger, so 2.5 millimeters. Okay, so now I can bring in the eyepiece lens. And so if I want to be able to comfortably look into this microscope with relaxed eye muscles, I need to have the image created by the first lens at the focal length of the second lens. So that means I need to choose the spacing between the two lenses such that the total distance is equal to the distance to the image, right, which was 130 millimeters, plus the focal length of the eyepiece, which was 50 millimeters. So that means my spacing between the two lenses is going to be 180 millimeters. In a real life microscope, you have a little barrel adjuster that changes the length of the tube so that you can get a resulting image that's comfortable to look at. Okay, so the last part was trying to figure out the angular magnification of this pair of lenses. So I want to identify the angular size of the object and the angular size of the image. So the angular size of the object I could find in two different ways. I can either look at the angle created by this triangle over here. So that would be the tangent would be the height of the object over the distance to the object. I could also look at this triangle here with the base of 130 millimeters and a height of like 25, I think it was, or 2.5 rather. Both of those would give me the same angle, and I get that the angular size of the object is going to be about 1.1 degrees. For the angular size of the image, then I'm looking at this angle, or this triangle here, where the base is the focal length of the eyepiece, and the opposite side is the height of the intermediate image. So the tangent of that angle is going to be the height of that image, so 2.5 millimeters over the focal length, 50 millimeters, gives me an angular size of just 2.86 degrees. So the angular magnification is going to be the ratio of the angular size of the image over the angular size of the object, which gives me 2.6. So if you've ever used a microscope, you see it says something like 50x or 100x or 200x on the side of the microscope. That value is typically given as the angular magnification times the linear magnification of the first objective lens. So we had 2.6 here, and then we had a linear magnification of 25 on the I think that was right, 25, yeah, 25 on the objective lens. So my total is going to be 25 times 2.6, which I'm going to embarrassingly try to do in my head, and I think is going to be like something like 65 or 64 or 65x. So if you had this actual microscope in your hand, it would probably have like 65x printed on